Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, in our previous two sessions, we talked about atmospheric radiation. We talked about how atmospheric radiation is caused, what are the parameters to identify, to calculate the radiation in the atmosphere. We discussed about the Wien's law and many other aspects of atmospheric radiation. Today also we are going to talk on atmospheric radiation in an elaborative form, and for this we have again with us in our studios Dr. Arun Kumar Srivastav. Dr. Arun Kumar Srivastav is Assistant Professor in School of Environmental Sciences, Jawaharlal Nehru University. So first of all, I would like to welcome our guest Dr. Arun Kumar Srivastav, and with the help of his extreme knowledge, we are going to understand more about atmospheric radiation. Hello sir, welcome to the EduSet lecture.
Thank you very much. Good afternoon friends. Today I think we will continue the previous lecture, previous discussions, and that was on atmospheric radiation. In the first lecture we discussed about what is atmospheric radiation, how it is caused, and what are the different methods how it propagates into the atmosphere, how it becomes the part of our atmosphere. In the second session we discussed about different methods, how it is scattered, how it is spread into the atmosphere, what portion comes to the atmosphere, what doesn't, and how it is, if it is not completely coming to the Earth's atmosphere or at the Earth's surface, how it is trapped, what are the different parameters which actually absorb or traps the different portions of atmospheric radiation. In fact, the atmospheric window, and what are for which radiations the atmosphere is transparent and for which radiations the atmosphere is opaque, some atmospheric window, etc. In this particular session we will discuss, now we are of this opinion that radiation is there in our atmosphere, how this atmosphere is, how atmospheric radiation is budgeted, what are the different parameters which govern the budget of radiation into our atmosphere. Now starting with this picture, we will see here sun radiates energy, although it radiates energy in all the direction. In one of the directions Earth is there. Since Earth is far off from the sun, the distance between Earth and sun is very much, although sun radiates the radiation in an spherical manner, in an spherical direction, in all the direction. So the direction is radial, but because of the distance, since the distance is very much, so the radiation falls on the Earth's surface in a parallel manner. So, and in fact it falls on one of the surfaces, one of the face of Earth, and the remaining half is dark. It doesn't exposed by the sun's radiation. So after 24 hours, that particular portion of the Earth is radiated by the sun's radiation. So the radiation becomes, although it is originally in a radial direction, but in the later stage it becomes in a parallel manner. So in parallel manner it strikes upon the Earth, but it doesn't exactly strikes on the Earth's surface. It strikes upon the Earth atmosphere system. It strikes actually the top of our atmosphere. So what happens when it strikes upon the Earth's surface, top of the Earth's atmosphere? The flux which strikes at the Earth's atmosphere's top is actually 1370 watts per meter square. That is also known as Earth's solar insolation. Earth's solar insolation, it is indicated by Fs, and although we know the Earth's cross section area is pi a square, whilst the Earth's albedo is 0.3 in fraction, it is represented by A and its value is 0.3, or in other words we will say that it is 30%. What does it mean actually? I think we have discussed in elaborate manner in the previous class that this 30% are the part of solar radiation which is completely reflected back to the space. It doesn't have any bearing on the Earth's atmosphere. So only 70% remaining reaches to the Earth atmosphere system. So in this manner the incoming solar energy becomes 1 minus A, 0.7, into Fs pi a square. Now, according to the Stephen Boltzmann's law, what we have discussed in the previous session, power emitted per unit area is equal to sigma T to the power 4. Power emitted in all directions from total surface area is equal to 4 pi a square. So, total power emitted by the sun towards the earth is 4 pi a square sigma T to the power 4. Now, if we assume that the earth is a complete black body, then what will happen? Incoming energy is outgoing energy. I am sorry, this pi a square is pertaining to the earth's surface area. So, the incoming solar and incoming energy should be exactly equal to the outgoing energy. Therefore, it's 1 minus a Fs pi a square should be equal to 4 pi a square sigma T to the power 4. If we solve this, we will finally find out that T, here T what given in this formula, should be approximately equal to 255 degree Kelvin. But if we measure the temperature of the earth's surface, that is not exactly 255 degree Kelvin, but it is 288 degree Kelvin, approximately approximately 33 degree Kelvin more. So, where is this? I mean, what is the problem? How it is happening? Why this disparity actually? So, just to find out this, I mean, this disparity is will actually lead us to many nice and many important atmospheric phenomena, that is known as greenhouse effect or greenhouse effect phenomena. So, in fact, if we model this greenhouse effect to solve that issue, why this 33 degree Kelvin temperature is more, which we observe at the earth's surface. If we have here, we have illustrated a diagram of earth and atmosphere system. Atmosphere is represented in light blue color, while earth's surface is represented in brown surface. Here we will see at the top of the atmosphere, the solar flux is represented by F0. If there is some coefficient which is because of the attenuation of the atmosphere, I mean solar radiation is to some extent is being attenuated by the atmosphere and the remaining is left, I mean coming towards the earth, then the F0 which is coming from the top of the atmosphere of the solar radiation will become tau s into F0. So, the sun's radiation which strikes at the top of the atmosphere will pass through atmosphere and will reach at the earth's surface as tau s F0. Now, what happens when the earth re-radiate the energy or radiation? It is radiating a energy flux of Fg, and after attenuating, I mean that Fg is getting attenuated by the atmosphere and the remaining which comes out of the atmosphere is tau T Fg. Here I think we have discussed in the previous sessions also that there is a one very important thing that one should keep in mind while when we discuss about the earth's radiation budget, is that the solar radiation, although it comes in the form of short wave radiation, the most of the radiations are in the, as far as its wave nature is concerned, either it is in the visible range or some portion of the infrared region which is near infrared and very small amount from the UV ray region. So, mostly 100% comes into the form of short wave radiation, whilst when it goes back after striking the earth's surface, it goes back in the form of long wave radiation. Long wave radiation, I mean where the short wave radiation finishes, here in this particular case, long wave radiation starts from there. I mean the long wave radiation which goes from earth's surface is mostly in the form of infrared waves, and that is in the far infrared wave region. So, we will not find any wave, although it comes in the visible form, it comes in the near infrared form, or it comes some of them in the form of ultraviolet rays, but when it goes back, it goes in the form of far infrared region or far infrared waves. That is why here it is represented in the red colored arrow. Now, atmosphere because it is absorbing from both the sides. It is absorbing the short wave radiations which is coming from the solar side, as well as the radiations which is going from the Earth's surface. So, that is in the form of long wave radiation. So, our atmosphere has also its own energy budget. This energy flux here is represented by Fa. So, atmosphere is emitting a flux of energy in the which is denoted as Fa in both the directions, that is in the upward direction which is towards the space, and downward direction which is towards the Earth's surface. The atmosphere has its own temperature because of this, and here it is represented as Ta, whilst the Earth's surface temperature is represented as Tg. Now, here we will have to solve that problem what we have discussed earlier, that what the Earth is receiving at the top of the atmosphere is not exactly what we are receiving, what we are actually observing at the Earth's surface. So, to solve that problem, I showed this illustrated model. Now we will have to solve that model or solve that illustration here. In natural condition, layer of atmosphere exists, we all know, and the layer of atmosphere is because of the composition as well as the temperature and pressure profile. The temperature of atmosphere, if we, it is as although there is a layer, but here in this particular case we have assumed the temperature of the atmosphere as constant, and that is Ta. The atmosphere transmit fraction of any incident solar radiation tau s and fraction of thermal radiation tau t. Here tau s and tau t actually pertain to the short wave radiation, that is tau s which is coming from the solar side, and tau t which is here thermal radiation which pertains to the long wave radiation which is coming from the Earth's side. Now, what happened for the non-transmitted radiation? The top of the atmospheric irradiance F0 is here, it will become F0 equal to 1 minus AFS, while A is the albedo. F0 all we know is approximately 240 watts per meter square. Solar radiation which reached Earth's surface is tau s F0. Now, since we know the ground emit an upward flux, that is F0, which is equivalent to sigma Tg to the power 4. Upward flux which reached top of the atmosphere is tau t sigma Tg to the power 4. Now, atmosphere is not a black body, but emit radiation both upward and downwards. Atmosphere irradiance is Fa, which is equivalent to sigma Tg to the power 4 plus 1 minus tau t multiplied by sigma Ta to the power 4. Thus, incoming solar energy must be equal to the total energy emitted outwards from the Earth. Therefore, 1 minus AFS will be equal to the sigma Tg to the power 4 plus 1 minus tau t sigma Ta to the power 4. If we further solve this, then we will find tau t will be equivalent to sigma Tg to the power 4 plus Ta to the power 4 plus Fs multiplied by A minus 1 upon sigma Tg to the power 4. With the help of this, because all the factors present here are known and can be obtained somehow. So, if we solve this equation, we will find a value of tau t as equal to 0.77. So, this is a factor, and this 0.77 actually represents that 77%. What does this 77% means actually? So, it says that 77% of the total radiation which is emitted by the Earth is absorbed by the atmosphere. Thus, whatever the Earth re-emits towards the space, out of that 77% gets absorbed by the atmosphere. This explains why the temperature of the surface is higher than the input solar heating, what we actually expect, what actually should be, and explains the atmospheric radiative greenhouse effect. This is, this trapping of the temperature or radiation by the different component of the atmosphere is also known as greenhouse effect. This is why we get the higher temperature than anticipated at the Earth's surface. if the radiations were not being absorbed into the atmosphere by greenhouse gases and slowing the rate of cooling of the ground represented by tau T sigma T a to the power 4, the ground would be much colder than it actually is. Thus, it can be seen that if greenhouse gases increase, it results in an increase of the factor tau T, then the ground temperature will become even warmer. But naturally, I mean this should be balanced and the trapping should be constant. Therefore, the temperature which is trapped which is there by the trapping of the radiation should be constant. Finally, if we apply tau T to the above equation, if we put the value of this, it results in an atmospheric layer temperature which is T A equivalent to 227 degree Kelvin, which is equivalent to minus 46 degree centigrade, which is very close to the temperature which is found or which we expect at the top of the atmosphere. And if we further solve this, we will find a temperature at the Earth's surface as 288 degree Kelvin or 15 degrees centigrade. So, and this is the normal Earth's surface temperature. Here now we will, now how it is happening, I mean this so far we modeled this, we use the formulae and different constants and values to obtain or to show that why the difference is, I mean why the difference in temperature is there from the top of the atmosphere to the Earth's surface. Now, here it can be illustrated, I mean I have many pictures to show and to explain about this particular phenomenon. Here in this picture we have the picture diagram of Earth as well as the atmosphere, which is represented by light blue color. Now, we will see here, I mean this is the first of the picture, this is the easiest one, we will further elaborate it, we will further discuss it in a more explained manner. Now, here we will see that when the radiation is striking at the top of the atmosphere, a partial radiation is going at the Earth's surface. A significant amount of the radiation is exactly getting reflected back, which is approximately 30%, which we also call as albedo, while some portion is getting absorbed by the atmosphere. This is one of the things, and the second thing by which Earth is radiating the radiation towards the space. Here we will see, which is represented by blue color, a partial, I mean here a very significant amount is not passing through the atmosphere, but is getting absorbed into the atmosphere, and remaining portion is getting radiated back to the atmosphere or space, sorry, remaining portion is getting radiated back towards the space. Here, I mean here actually its bifurcation or its quantitative values are given here. I mean it is coded by 3 different colors. You can see here that the incoming solar radiation, which is approximately 340 watts per square meter, is striking at the top of the atmosphere. 48% is getting or it is reaching towards the Earth's surface, while 29% is reflected back, which is albedo, while 23% is getting absorbed by the atmosphere. This is a very broad, I mean a very general statement about the division or different components of the solar radiation. We will discuss it further here. I mean here it is in some elaborate manner. You will see here in the left hand side is given the energy loss from the Earth, while in the right hand side is given the energy gain from at the Earth's surface, which is naturally from the sun. So, now we will see the sun, which is giving energy or which is giving radiation to us. Some is being absorbed by the clouds, etc., or the atmosphere, which is some of it is getting absorbed by the atmosphere, while going back a very significant portion is getting absorbed by the atmosphere. There are 2 more factors you will see here in the right hand side. One is written as convection and conduction, another is written evaporation or latent heat. Now, I must explain this in detailed manner. What is convection and conduction heat? Here it is pertinent to mention that the convection and conduction is only possible by the long wave radiation or the radiation which is being emitted by the earth's surface. It is generally not possible by the short wave radiation which is which comes actually from the solar side. So, what is this convection and conduction? This is the energy or this is the radiation which is being actually trapped. This is also known as the sensible heating or sensible heat. This is the heat or radiation which actually is transferred to the different components of the atmosphere like gases etc., but because of this radiation or because of this heat, here it is conduction and convection form of radiation transport, but because of this heat which is being transferred to the components of the atmosphere, the nature of those molecules or atoms does not change, but they localized it. I mean, this is the heat, or in a simplistic manner we can say this is the heat which actually is responsible for the blowing of winds etc., because what happens when this heat, when this radiation hits the atmospheric components, the pressure is changed there, and because of that pressure change it is being replaced by the other gases which is not having that level of energy, and because of this what happens, winds start blowing. So, a good portion of that radiation which is being emitted by the earth is responsible for the sensible heating, which is responsible for the various climatological phenomena. Apart from that, a good amount is also involved or also used for the latent heat. What is latent heat? I mean, we know all this rain and cloud formation etc., how this cloud and rain formation takes place, whether it takes place by the heating of the solar radiation or the short wave radiation, or it takes place by the long wave radiation or the radiation which is going from the earth's side. It actually takes place by the radiation which is going by the earth's side or the long wave radiation. So, what does it do actually? It actually, when it goes to the water, it transforms its phase. I mean, the transformation of phase means initially it is liquid phase and later on it gets converted into the vapor phase. So, there is a phase transformation, and because of this phase transformation some heat is involved. Here in this particular case, when there is a phase transformation of liquid towards the gas, then the heat is getting absorbed or heat is being taken. But if there is a vice versa case, I mean, when vapor or cloud gets converted into the liquid form, then there is not heat absorption, but heat release is there. So, this latent heat is a type of heat which is used for the phase transformation. It can be positive, it can be negative. I mean, it can be for the gain as well as for the loss of heat. So, a significant portion of the long wave radiation is used for the latent heat or for the cloud formation etc., and as I told, a good portion is undoubtedly being absorbed by the atmosphere. So, now here we will have to discuss exactly how much portion or how much percentage is attributed for the different phenomena. Now, here in this particular case, elaborate description is there. You can see here 340 watts per meter per square meter of solar radiation strikes at the top of the atmosphere. Out of that, here the numbers in the bracket, it actually represents the range. Sometimes it is 340 and sometimes it is 341. I mean, it is a kind of annual cycle. So, it might change from 340 to 341. So, now we will presume here the bolder or the bigger letters, bigger digits. 340 is the amount of solar radiation which actually strikes at the top of the atmosphere. Out of that, 100 is exactly reflected back, which is approximately 30%, and that is the albedo. Out of, and now 240 is left. out of that 240, 79 is absorbed by the various atmospheric gases. Here I must say this is mostly absorbed by the smaller molecules like oxygen, ozone, etc. And now the remaining 185 strikes, it passes through the atmosphere and might reach the Earth's surface. But what happens, out of that 185, only 161 watts square per meter is able to completely or successfully reach at the Earth's surface. 24 directly goes back after getting reflected by the Earth's surface. So, in total, and this 24, initially I said 100, this 100 is because of the clouds as well as the Earth's surface. This albedo includes the clouds as well as Earth's surface. So, this in total is 100. Now, here we will say at the right hand side 398 watts square per meter, in fact, which is more than what actually Earth has received. Earth has received just 161 watts square meter, but here it is reflecting around 398, that is more than twice. So how it is happening? It is happening because it is, these solar radiations are also trapped into the atmosphere, and atmosphere, as in the very first diagram, which was the modeling of greenhouse gases I showed you, atmosphere starts working as a source. So atmosphere again starts giving radiation to the Earth's surface. Here it is 342 watts square per meter, and remaining 239 watts square per meter is finally able to go back to the space, but 239 is, again we will say here, is more what it should actually be. Now, how it is compensated? Here we will see that there are two factors, that is between the yellow arrow and the red arrow, and they are latent heat, which is because the phase transformation or cloud formation, as well as the conduction and convection, which is the formation of winds, etc., etc. So this is how the entire Earth's radiation budget is balanced, but we will further discuss it. We will give a more detailed explanation to this, and here it is detailed explanation by which we will have a clear idea. Now, we will see here that 342 is coming, 342 watts square per meter is coming, 77 watts square per meter is exactly, here you can say, see here in 77 watts square per meter is getting reflected back by the clouds, atmospheric gases, as well as the aerosols, and approximately 30 watts square per meter is getting reflected back by the Earth's surface. So, in total it is 107. Now, we can say out of 342, 107 is getting reflected back, and here it is again pertinent to see that 67 watts square per meter is getting absorbed by the atmosphere. So, now we are left with 168 watts square per meter, which is being absorbed by the Earth's surface. Out of that, 24 watts square per meter is used for the conduction and convection or the winds formation, and 78, a good amount, is utilized for the formation of clouds, etc. Now, what happens to Earth's radiation, which is now converted from shorter wave to long wave radiations? Now, Earth is emitting 390 watts square per meter. Out of that, 40 is directly going to the space. It is not hindered, it is not stopped by any atmospheric component or anything, but it is directly going back to the atmosphere. So, 350 is left, which is being trapped by the atmosphere. Out of that 350, 324 is getting back again towards the earth surface, and out of that 30 is going, I mean after getting filtered from the atmosphere towards the space, and 165 is emitted by the atmosphere, which is the part of radiation which was initially absorbed by the solar radiations too. So, now you will see here that approximately 235 is getting back to the, I mean that is outgoing long wave radiations, which is approximately 235 watts square per meter. And now you will see here there is some latent heat as well as there is some heat which is sensible heat of conduction and convection. We will, if we estimate it, we will find it that radiation is totally balanced. I think perhaps here it is furthermore clear. Here 100% is coming, 6% is reflected by the atmosphere, 20% is reflected by the clouds, 4% is reflected by the earth's surface, and remaining 70% which should reach to the earth's surface. Out of that 16% is absorbed by the atmosphere, 3% is absorbed or utilized by the clouds, while 51% is absorbed by the earth's surface as well as the ocean. Now, of that 51%, 7% is used for the as a sensible heating or conduction and convection. 23% which is at the extreme left hand right hand side is used for the latent heat or the clouds formation, while a good amount of approximately 15% goes back directly to the, it tries goes to go back to that space, but out of that only 6% is able to go back to the atmosphere. And from the atmosphere, now we will see here it is a combined effect of conduction convection, sensible heating as well as the radiations which are absorbed by the atmosphere. 64% is going back after getting filtered or after getting absorbed by many processes by the atmosphere towards the space. So, this 64% and 6% becomes 70%. So, thus we can say here that 70% is coming towards the earth surface and 70% is going towards the space. Here, I mean here it is the same picture by some other author, I mean more or less it is same, the same things are here. So, no need to explain it. I am sorry. Here we will see here, I mean here, I mean further a clear picture is there. 100 is coming, 16 is absorbed by the various atmospheric component. Here I must mention that initially the radiation is absorbed mainly by the water vapor and dust and ozone, 3% is absorbed by the clouds. So, 51% is reaching, while 4% is reflected by surface, 20% by clouds and 6% by is a kind of back scattering by air, which is Rayleigh scattering, what we had discussed in the previous session. So, 51% is getting absorbed, and of that 51%, 21% is going 21% is going towards the space, but of that 21%, 15% is absorbed by water vapor and carbon dioxide. So, left 6% is going towards the space, and when some heat is being emitted by the atmosphere, and finally that net emission becomes, I mean that is by H2O and CO2 is 38%, and 26% emission is there by clouds, which originally took around 23% as latent heat, and 77% is the sensible heat. So, how this Earth's radiation budget is balanced. This is again another picture. If you want to see if you are still not able to understand it, so now you can see here that 342 is coming, 67%, 342 is coming, 107 is going, and 40 is here, 235 is here. Now it is divided into short wave radiation and long wave radiation and convection. There are three different sections, you can say, short wave, long wave and convection. In short wave, towards the space we have 342 which is coming, 107 which is reflected or which is albedo, 40% is from the surface emission or surface emission transmitted through the atmospheric window, and 235 watts per square meter is atmospheric emission. Now if we add these four, we will find, because 342 is minus because it is given to the earth and remaining is taken by the space. So now this equation is balanced, 342, 107 and 40 and 235. So finally it is becoming 0. If we come to the atmosphere, now we will see here that 67% is absorbed by the atmosphere, 77% is absorbed by the clouds, gases and aerosols, 30% is reflected, or sorry, not 30%, but 30 watts square per meter is reflected by the surface. And here what happens in the atmosphere for the longer wave radiation, 350 is absorbed by the various components of the atmosphere. They are CO2, especially CO2 and H2 and clouds. So now if we calculate this here, we will see, because 235 and 324 is given to us, so it is in the minus, and 350 and 67 is given towards the space, so it is positive. Now if we calculate it, finally we will get here minus 102. So now minus this minus 102, because here the balance is more or less disturbed, it is minus 102. So now how this will be balanced? This will be balanced by the sensible heat and latent heat, which is 24 and 78. This 24 and 78 becomes 102. So this 102 plus and minus 102 which was in the atmosphere becomes 0. So now here in the atmosphere this radiation budget is also balanced. Now we will have to look at the surface, what happens at the surface. At the surface 168 is absorbed, 168 watts square per meter is given by the sun, and 390 is going away, 324 again earth receives from the atmosphere. So 168 and 324 is positive because it is given to us, and 390 is given away. So this is minus 34. Again we are getting here plus 102, which is again it shows that there is a disbalance. But if we take the direct heating, which is 24 of the atmospheric components for the sensible heating or for the conduction and convection, and 78 which is given by the earth for the evapotranspiration or the cloud formation, then if we add these two, which is minus because it is given away by the earth, so minus 24 and 78 it becomes again minus 102. So minus 102 and plus 102 is again 0. So now we can see here in all the three parts of the atmosphere earth system, which is space, atmosphere and surface, and including two type of radiation, which is short wave radiation and long wave radiation, and also the convection. We can see here in all the three parts of the earth's atmosphere system the radiation budget is balanced. But what happens now, this what we discussed so far is basically, it is when there is a ideal condition, or when the environment is absolutely natural, which is not anthropogenic, which is not disturbed by any other component or any external agencies. So what will happen when the earth is, not absolutely in natural form, but it is disturbed by the external agency? Now we will have the forced radiative forcing. Like what are those parameters? Now we have discussed, because these Earth's atmosphere's different parameters, especially the CO2, H2O, CO, clouds, etc., are necessary to have some optimum temperature, because if there would not have been atmosphere or atmospheric component, the Earth would be much colder than what we are having now. In the morning period or in the day period, it would have been very hot, and in the evening or night period it would have been very cold, and the temperature would have been in the minus. So there would not have been possibility of any life on the Earth's surface, like what happens on other planets where there are no atmosphere. So in the day period the temperature is very high, sometimes it can go it generally goes to more than 100 degrees centigrade or 200 degrees centigrade, whilst in the night time it goes to minus 100 or minus 200 degrees centigrade. So the same condition would have been on the Earth's surface, and because of that life would never have been possible on the Earth's atmospheric system. And because of these atmospheric components or the presence of atmosphere, life is possible as well as life is thriving on the Earth. But what will happen if there is inclusion in those atmospheric components? I mean, if the atmospheric components, because of some external reasons, are getting included into the atmosphere. So this will create a forced radiative forcing, which is also known as additional or forced radiative forcing. Now first we should have some information about the radiative forcing. What radiative forcing exactly is? Radiative forcing is basically a change in the net radiation at the top of the atmosphere due to some external factor. Now net radiation should actually, what we discussed and what we have seen many pictures, with the help of that we understood that the net radiation should exactly be balanced. I mean, incoming should actually be the incoming amount of the radiation should actually be the outgoing amount of radiation. If it is not the case, and if incoming is more than that of outgoing, so now we'll see, then we'll say that the radiation is a positive radiation. I mean, the net radiation is positive net radiation. If the case is vice versa, I mean, when the outgoing radiation is more than that of incoming, so the net radiation is negative. And this is why when there is a positive net radiation, we say that there is a positive radiation, or the case is warming. If there is a negative there is a negative net radiation, we will say that there is a negative forcing, or the result will be cooling. But nowadays we are having the previous case, I mean, which is positive forcing, I mean warming, and everyone is concerned about the global warming. Here we will discuss or we will see what effects, I mean what effects can be there on the forcing of radiation when there is an inclusion of additional gases. I mean when the balance of the atmospheric components are disturbed. Now we all know that atmospheric CO2, which is a major component as far as the radiation absorption, especially the infrared or outgoing radiation is concerned, the amount of CO2 is continuously increasing, and it is significantly increasing after the industrialization era. If we have the graph since 1750 to up to 2000, we will see that from 1750 to up to 2000 there is an exponential growth in the concentration of carbon dioxide, which has, I mean the increase in the tunes of millions of metric tons. Now if we further zoom it down, we will see here from 1955 to 2005 there is a sharp rise in the atmospheric CO2 concentration. If we take it into the ppm, we will see that it has increased from 320 ppm to 380 ppm. I mean, there is a very significant increase in CO2 concentration in the units of ppm. Here it is important to mention that if there is an increase of 1 ppm, it is, we can't ignore it saying just 1 ppm. 1 ppm indicates a million metric tons of inclusion of CO2 into the atmosphere. Here, and we all know that there is a very significant and very good correlation of the atmospheric CO2 with the global temperature. Now, here in this picture, how the temperature is changing as well as how the atmospheric CO2 concentration is increasing. Now, we can see here there is, as I mean, this temperature increase is following the CO2 concentration increase. I mean, it is in temperature is, we can see here temperature was somewhere approximately minus 2 degrees centigrade or so, and now it has gone to approximately 1 degrees Fahrenheit, whilst the global CO2 from approximately 280, it has gone to approximately 380 degrees centigrade. Now, 380 ppm, I am sorry. So, we can say here there is a very good and positive correlation between atmospheric CO2 and temperature. So, if CO2 increases, the temperature will definitely increase. Now, what will happen if there is a CO2 increase? Now, we will calculate the radiative forcing of the CO2. What will happen and how it changes. Suppose in 1965 CO2 concentration was 320 ppm, in 1990 it has become 355 ppm. If we assume exponential growth, the formula can be written as C equal to C0 e to the power RT. C is 355 and C0 is 320. If we put, now we will find R is 0.41% per year. I mean, we can say that there is an increase of 0.41% of 0.41% of CO2 every year, but this 0.41%, one should keep in mind that the growth is not linear. So, this 0.41% is not constant because it is an exponential growth. So, next year it will change, again it will change significantly. If this rate continues, then what time will it take to double the amount of concentration of CO2 in the atmosphere? Now, we should calculate here. If the rate is, and 280 we have taken the initial value of CO2 because 280 ppm was the concentration of CO2 during the pre-industrialization period. With the help of this, we can calculate T as 110 years. Say, so we can say in year 2100, I mean from now onwards, after 85 years, we will have amount of CO2 doubled, exactly doubled into the atmosphere what it was during the pre-industrialization period. If this rate continues, we can the time taken to double is, I mean here we have calculated is 2100 in year 2100. So, what will happen when the CO2 is doubled? What will happen to the temperature? Now, with this formula, delta T equal to delta T double upon ln2 into CO2 T and CO2 0, we can calculate the temperature. It comes here 1.5 degrees centigrade. Although it is 1.5 degrees centigrade, but it is far more because during the dinosaurs period, this temperature was minus 4.5 degrees centigrade. Now, if we even, so there is an increase of 6 degrees centigrades in the temperature. So, we can say here that this delta T, which is 1.5 degrees centigrade, is the warmest temperature in 10,000 years. So, in 2100, if the rate what we are presently having, if the rate continues in 2100, we will have an increase of 1.5 degree centigrade. So, I think with this we should finish it, and if possible the remaining portion we will discuss in the coming sessions. And so, thank you very much with this.
With this note, thank you, sir. Thank you so very much for giving us a very productive session. As you yourself, with the help of the numerical formulas, helped us in explaining how the atmospheric radiations can be detected and they could be known in the atmosphere. So, sir, there are any parameters available with the help of which radiations can be calculated or measured?
Yeah, there are many instruments with the help of which radiation can be measured, solar radiation as well as, because solar radiation is in the form of short wave radiation or visible, what we see. With the help of this we can see, but earth also radiates energy or radiation, and that is in the long wave radiation, and which we can't see, that is in the infrared region, in the infrared region of the spectrum. So, this both the radiations, whether it is coming from sun or whether it is going out of the earth. So, both the radiations can be measured using sophisticated and using required instruments, and there are different units for this monitoring and measurements, and in fact, there are different monitoring stations across the world which are continuously monitoring the solar as well as the outgoing Earth's re-radiated radiation, which is also known as thermal radiation.
If you talk about the human beings, then how human beings contribute in the cause of radiation to the atmosphere?
This I told you that because of the human being and deforestation, I mean we have some formula and we can discuss in later sessions that because of the human being, I mean this population increase, CO2 is increasing, as well as the deforestation is taking place. So, the concentration of CO2 is continuously increasing into the atmosphere, and in one of the pictures I showed this concentration of CO2 is having a positive correlation with the temperature. So, the CO2, if CO2 increases, the temperature will increase, and although just 1.5 or 2 degrees centigrade is not much, but this 1.5 or 2 degrees centigrade increase in temperature is very significant as far as the melting of ices, melting of glaciers, etc. are concerned. If once the buffer, I mean buffer zone or that limit is crossed of the temperature limit which is stopping the glaciers to melt, if it is crossed, the glaciers will start melting, and this will be fatal, because this glaciers melting etc. can lead to the sea level rise, and sea level rise is again very fatal. I think I have discussed in the previous classes that sea level rise might lead to various disasters, especially to the nations or cities which are in the coastal region or which are near the ocean.
With this note, thank you, sir. Thank you once again for your delivery, for the inputs you have given to this lecture. And dear friends, we would be meeting again very soon and would be discussing more on atmospheric radiation. Till then, you can watch this lecture with the help of the YouTube, which we are going to upload very soon. I mean, we are going to upload this lecture very soon on the YouTube, with the help of which you can access it with the number of times you wanted, and you can of course mail us your queries at info.cc@nic.in. Till then, take care, goodbye. With this note, thank you, sir. Thank you so very much.
Thank you very much.